just to summarize, this technology, as said before, has some special features that can be pretty interesting for the future applications. As said, modularity is, let's say, a must. It's a must for scaling up with the de-risking, without increasing risk for the scaled up operation. We can easily scale up the system based on these present results, because mainly all the components that we have tested here in terms of manifolds, injection nozzles, heat exchangers, electrical heaters will be kept pretty the same if the system will be 5, 10, 20 times larger, because this is just the system that will be enlarged, but keeping the same components as they have been designed and tested so far. Second feature is about environmental friendly materials. As Piero was also mentioning, system is renewable, but also material must be, let's say, green and possibly recyclable. If we think about in terms of life cycle assessments, we are using only steel, sand, no special materials that can be a problem if must be disposed of. Storage media, as said, is a solid particles with the fluidization, which is a peculiarity, which can give us the possibility to take the temperature pretty high and to fluidize to enhance, as explained by Piero, the heat transfer coefficients and make the system compact and efficient. Charging time, if we think about competitiveness, we say that if we want to take, and also Mr. Dott was explaining, there are sometimes a few hours in the day where the electricity is curtailed, or where the electricity has a pretty low cost, zero cost, or even negative cost sometimes. So we can take those slots of times pretty fast. We are writing less than 6 hours for charging, but really the system is designed to be charging in 4 hours completely. The response time is also an advantage, a consequence of the fluidization. When the system is fluidized, it's pretty reactive, thanks again to the high heat transfer coefficients. And this is giving also some advantage when you start up from 0 to 100% load, and again, when you have to shut down the system from 100% load to 0. And the storage duration also, we can, let's say, design the system for most cases with the daily cycles. But in case the system has to be stopped for some days, it can happen in some industries the weekend, or some days the plant cannot be maybe receiving steam. We can shut down the system and keep the heat inside with very minimal heat losses. So given that, let's see how this system is made. This picture is showing this. We have here on our roof a photovoltaic system, 2 megawatt electric here installed. So we are charging this system with electricity from our renewable PV plant and sometimes from the grid. We have 450 kilowatt installed here with a sand mass of about 40 tons. We have been changing the mass of sand to make different arrangements. In this moment, we have around 35, 36 tons. And we have been designing the system to produce steam in the range of 200, 190 degrees flat. But we can also produce steam with this system at 300 degrees. The system, as said, started this operation around 2-3 years ago. In this configuration, after some changes, after some optimization that are still going, we have been producing steam in the latest 1 year. So the system, this Alpha 4, we call Alpha 4. It's a pilot, but it's including all the subsystems that will be necessary in future industrial plants. The major system, as he said, are the fluidized bed module with the integrated electrical heaters. You can't see here because they are mounted on the roof. They are hanging into the sand. The second system is the fluidization air system. You can see on the back the air heat exchangers, and outside there are the blower and the fan and the filter. Inside the system, we have the steam generation system. If once through heat exchangers that takes the fresh feed water from the outside and evaporates and transforms it into superheated steam. And finally, we have all the instrument and control for automation and logics. So the system is complete, it's completely representative. Also important to mention is that we have equipped this pilot of a full set, a lot of sensors, thermocouples, pressure transmitters, flow meters, both for the airflow and also for the water and steam flow, to try to understand all the parameters, the operational parameters. So we have been recording in the past months and years all the data to be able to check how they are working and how they can be working. One of the tasks of Magaldi that is also in our logo is to have reliable technologies, to provide to customers reliable technologies. So we have to be sure that all the components, each component is working properly and all the system is working properly. So let's see some results. We have been working, I will not be too long, but let's say just see some results. We have been making repeated operational tests in the latest 1 year in this configuration. This testing campaign has been able for us to validate and to provide very interesting results, to validate the system operation and also to evaluate the performance and the reliability. With these, all the phases, charging phases, hot standby, let's say hot standby, we mean when the system is not fluidized at its maximum temperature of 620 and is shut down, we see how are the heat losses. And then during, of course, the discharging phase for steam generation, and also the so-called cold standby, when the system has reached its minimum temperature, of course, we have also to observe what is the behavior of temperature losses. So just some diagram, you maybe can't see, but the first diagram is some tests made just 1 year ago, October 2023. The blue line is the same temperature during steam generation at 200 degrees. So you can see that the system is decreasing the temperature. Blue line is going from 620 down to around that case 350. And the red line is representing the steam temperature. That is, as you see, when started, is going close to the same temperature, and is coming out to see from the system at a temperature very close to the same temperature. So the steam temperature, as it comes out, has a profile which is pretty similar, decreasing, as is the same temperature decreasing because it's discharging. But in the other slides, you can see, for example, on the right, when we introduce the superheating, I was mentioning before the superheating, most industrial cases, of course, need constant temperature and constant pressure. So we automatically mix a certain amount of fresh feed water with the superheated steam in order to get constant temperature. You can see, for example, the other tests are done with the green line is showing the steam generation temperature at 200 degrees. That is pretty flat after a certain transient time. Also, the transient time is pretty short. It's less than 20-30 minutes and can be still optimized. We have made also several tests with different flow rates, from minimum flow rate, in this case of 0.07 kilograms per second, to the maximum of 0.15 kilograms per second. And we have making also tests of ramping up, ramping down, to understand how the system fluctuates from minimum load to maximum load. Let's see next slide. This is another example, more recent, just a few weeks ago. We have been receiving, let's say, a visit. We are performing, let's say, a third-party validation performance test with a third company, which is a Fichtner from Germany, so that we can, let's say, have also a sort of third-party validation of the operation. This is just a test of a repeated 3 cycles of tests, ranging from a minimum temperature that was set for this test of 330 degrees up to 620, heating up the sand with the 450 kilowatt and producing steam at a flow rate of 0.1 kilograms per second. You can see the red line is the power from the electrical heaters. 3 days in the morning, charging the system. The blue line is the average temperature of the sand going up from 330 to 620. On the contrary, during steam generation, you can see the green line, steam generation, the continuous one, in the bottom at 200 degrees, 11 bar G, which is a temperature that will be used for our next industrial plant, just this temperature. And you can see that the sand is going down again with its temperature. So it's a cycling operation. In the same time, going up and down, like an electrical battery, but rather than having chemical reaction, as Piero was saying, we have a sensible heat. So when we charge the system, temperature increases. When the system is discharged, temperature decreasing. The superheating system is working, so we can ensure constant temperature at the desired temperature and pressure according to the, and as said, we are targeting application from 150 to 350 degrees so far, which are covered by this system, pilot system. So after that, in parallel, we have developed a thermodynamic model of the system, which is able to make this, let's say, all these transits of heating, cooling down, heat exchangers, so taking into account the heat losses. So by means of this thermodynamic model, we can predict and we can size the next applications. We are already working for several feasibility studies with potential customers. So it's important that we have the availability to use a system that is able to provide the potential customer with the expected steam generation according to any kind of a profile of electricity charging. I said the electricity charge can be both from a dedicated photovoltaic with its characteristic daily profile or monthly profile according to the site, to the GHA of the PV system, but from the wind and also by the electricity. So when we have an availability or in the year of electricity profile, we can simulate what is the system behavior, we can size what is the capacity, and we can provide the customer with the expected results. So let's see now what will be next. This is working. We have done it. We have been working and we have made several tests. We are ready for the next industrial application. This next industrial application will be just a site here. There is here on the left, here on my left, a company which is called Igi. It's an oil refinery, food oil refinery. They are working for the Ferrero Group, the company which is producing Nutella, the nuts cream. So it's important to keep it very fine. And we will be producing steam, green steam for the refinery of the palm oil. This also is a project done with cooperation NLX. In the next slide, let's say basic data will be basically a system in terms of capacity, of thermal capacity and sand amount 2 times bigger than this. You can see the gray line will be erected just 100 meters on that side and taking the water from the existing plant and producing steam back to the existing plant. The power input will be 4 times larger than this. That means that will be, whereas this system has been charged in about 8-10 hours, that one will be charged, as said before, in 4 hours, just to be able to take the most advantageous hours with the lowest electricity cost. And the steam will be produced according to their need at 195 degrees, 11.5 bar G. So just to take also the chance to have, let's say, the presence of many people from SolarPACES. In the SolarPACES, we'll be giving a presentation similar to this one in the topic of a solar industrial process heat application. We have been also studying the possibility to integrate our system, not only with the combined heat and power system, as said in my previous speech. Combined heat and power systems are efficient, but can take advantage of this. But also we can hybridize our system with concentrated solar power and any kind of Fresnel type or parabolic trough. If there is an application of this type with a solar thermal producing green steam, that's good. As well as it's good if there is if there are heat pumps. But with this system, we can provide further features. So it's important also to combine technologies together to find a way to give the best to the customers. By hybridizing this system with also solar thermal, the system may gain, let's say, advantages in terms of higher affordability and attractiveness, thanks to the storage capability and thanks to the possibility to take electricity at low cost, which is increasing the capacity factor of a system that can rely only on the sun. Direct sun may be not enough. Again, so this was already shown before, we can go on. So just to summarize before closing this speech, our message is that after this experience, the fluid bed technology for storing the heat is ready, both for concentrated solar thermal and also with electricity charging. We find in this power to heat solution a lot of advantages for the market. The system is modular, the system is standardized and resource efficient, it's pretty dependable and safe. There are no risk of corrosion, no risk of fire. It is also pretty easy to be put plug and play compared to a concentrated solar thermal power. We don't need all the rheostat field, we don't need the panels. The system is pretty compact. The electricity to charge the system, this system can be brought with a cable. So in the industry, maybe 90% of cases, maybe 95% of cases, they don't have place to install mirrors. So to charge the system may be troublesome to charge system with the solar power. But with this system, we have a compact system. We can charge, so it's pretty easy to plug and play. And I say it's pretty flexible because it's integrated to the grid. So final message, with the next slide, is to consider all together with you the features of the heat storage for the decarbonization of heat. There is a must. Heat must be in the industry decarbonized. This is a system offering possibility to do today 90% efficiency conversion from electricity to heat, green electricity to continuous heat. The possibility, second step, is to optimize heat generation cost. As also Mr. Dotti was mentioning, the system must be nowadays competitive. Otherwise, maybe a very nice solution cannot be implemented. But with the possibility to select the best hours, we can make, let's say, also reasoning about price arbitrage to select what are with also an energy management system. We are working, maybe we didn't mention it before, this system is also, let's say, supervised by an energy management system. Energy management system can be able to select what is the best time to charge the electricity with the lowest cost and to provide the steam when it is requested. This will be adding some values in the economics. And finally, also from the perspective of the transmission system operators, as also Mr. Dotti was saying in the previous speech from Alberto Toril, this massive introduction of photovoltaics and wind power will be potentially a problem for the grids. So the grid must be having not only electrical batteries, but must be also, can be also provided with system like this, which will be considered like a sort of a well where the electricity, surplus electricity, can be introduced when it is surplus, when it is in excess, and be taken back to produce steam and decarbonize the energy. So the three factors seems very reasonable to be put together to provide in the future possible many applications for the industrial decarbonization.